So I welcome everyone to the Power Electronics lecture series. So in the previous session, we have seen the example of chopper. So where the semiconductor is operated either in cutoff region or in saturation region. So when the switch is operated in cutoff region, so the output voltage is equal to 0. And when the switch is operated in saturation region, that is fully on, so that time output voltage is equal to Vs. So because of this advantage only, we discussed that the power electronics operation is going to be more efficient. So we already seen the definition of power electronics. It is application of power semiconductor to control and conversion of power efficiently. So what is motivated here means the efficient power conversion, where the semiconductor is operated in a manner of switching. So when it is fully on, the current is there in the switch, but the voltage is equal to 0 ideally. When the switch is fully off, the current is equal to 0 ideally, but the voltage is present across the switch. If you see, the resultant power consumed by this regulating device is 0. So that's why we employ these switching semiconductors in the power conversion. So that is what the power electronics, and we are going to observe the efficient power conversion. So we have seen this example, right? Chopper is there. So input to the chopper is Vs. The output of the chopper is V naught. So where V naught is a regulated one. So how we are doing the regulated output voltage means when I turn on the switch, the output voltage is equal to Vs. When I turn off the switch, the output voltage is equal to 0. So if I take average of this waveform, so we can able to get V naught equal to, so Vs into T on divided by a total time period. If I say this is capital T from here to here, so V naught equal to Vs into T on divided by capital T. So this is what we have seen in the previous session, and we have seen with some numerical values also, where the output voltage we can able to regulate by regulating the switch turn on instant. So what is the drawback here? What is the drawback here with respect to the chopper? So if you observe the output voltage is not uh, continuous. So you can see till T on, the output voltage is equal to Vs. After T on, during the duration of T off, the output voltage is 0. So this type of voltage supply is not recommended for the loads. So we need a continuous output voltage, and that too it should be regulated one. So to do that, we need to use uh, a device called as inductor. So to make a current continuous, so obviously I need the current and voltage should be continuous at the output side from the chopper. So now to make output voltage continuous, so we are going to use capacitor. We already know about capacitor. Capacitor doesn't allow sudden change in the voltage. So once the switch is turned on, so the capacitor is charging to certain value. So when I turn off the switch, whatever the charge stored in the capacitor, it supplies to the load. So you know, right, the capacitor doesn't allow sudden change in the voltage. So that is what the capacitor is doing here. So even though I turn off the switch, so it tries to maintain the same voltage whatever it is charged. Since we are operating the switching in microsecond duration, so we can approximate the output voltage is almost constant. So during switch turn off case, the capacitor discharges to the load. So this is how you can maintain the output voltage continuous at the load side. Similarly, if I want to take continuous current from the chopper, so here I need to use an element called as inductor. So you know the inductor doesn't allow sudden change in the current. So when I turn on the switch, what is going to happen means inductor starts charging with the supply voltage. So as you can see the KVL here, so the supply voltage is feeding to the inductor and the output voltage. So inductor starts charging. So now suddenly when I turn off the switch, as you know the property of inductor doesn't allow sudden change in the current. So if I take the current direction of the inductor is towards the right side, so it tries to maintain the same current direction. So here we are using these passive elements L and C, L and C to maintain the continuous current at the output and at the same time continuous voltage at the output. So this is how we use this L and C to have a continuous supply at the output. So but if you see this circuit is not complete. As you can see, when I open the switch, inductor, I said it is charging when the switch is in on state. When I open the switch, when I close the switch, it is in charging state. When I open the switch, so inductor tries to maintain the current in the same direction, so it discharges. It discharges. However, you can see in the above circuit, there is no path for the discharging. So the path is not there as I open the switch. So definitely you need to create a path to discharge the inductor. So that is where you are going to connect a diode in this manner. So you can see the diode connection. It should be connected in this direction only so that inductor can discharge in this path. So this entire circuit we are going to call it as a buck converter. So I'll prove that why this circuit is called as buck converter with some mathematical derivation. So right now you can see here. So input voltage is here to this entire converter system. So you can check after input voltage the supply is connected in series with a switch. Okay. So and then there is a diode and then there is a inductor, there is a capacitor. So this capacitor is connected across the load. So basically L and C tries to maintain continuous current for the inductor case, whereas continuous voltage for the capacitor, which is connected parallel with the load. So this converter, we call it as a buck converter. So now let us see the operation of this buck converter with some modes where in the mode 1, when I turn on the switch, when I turn on the switch, as I said, inductor is in charging state. So if you apply KVL in this loop, so let me take the current direction like this as a reference, and at the same time, the inductor polarity as a reference here plus here minus. So now if I apply KVL, so I can write a plus Vs. So let me take the inductor voltage as VL. So plus Vs minus VL. So minus V naught equal to 0. So here, here plus, here minus at the load side. So as the capacitor is connected parallel with the load, so the output voltage is equal to capacitor voltage. So from this, I can write VL, the voltage across inductor as Vs minus V naught, where Vs is the supply voltage, V naught is the output voltage. So now this equation we have written in mode 1 where inductor is in charging state. So if I ask you to draw the model waveform, you can check here. So when the switch is turned on, so here the gate pulse is there. So let me take the gate pulse here. So when the switch is turned on, okay. So if I take the gate pulse here, okay. So as I can see here, 0 to T on. Okay. So switch is turned on. The voltage across inductor is going to be Vs minus V naught. So voltage across inductor is Vs minus V naught. Okay. So the inductor is in charging state. Inductor is in charging state. So try to remember here. So these graphs are steady state graphs. So you may be getting a doubt at starting, where is the inductor current? So when I turn on the power converter at starting at t equal to 0, if I say, so that time inductor current is going to be 0. So you might be getting doubt. So it is starting at time in. So how it is possible? So at starting, current starts from 0 only. So it goes like this. It goes like this. So after some time, it reaches to steady state. So these steady state graphs we are seeing here, these steady state graphs we are seeing here, where the minimum point is I min here. So inductor is charging from the minimum current point. So I min, so it is in charging state with a rising slope. Inductor current is charging with a rising slope. So this is what you can see with respect to inductor. So now let us write the KVL equation again when the switch is turned off. So when the switch is turned off, you can check here. So inductor current direction is in this manner. Okay, so now it tries to maintain the same current direction and the same magnitude. So anyways, it discharges as the supply is disconnected here. So you can see the discharging path is going to be like this, where the diode is going to be forcefully turned on with the discharging of the inductor. So the discharging current of inductor is going to pass through the output voltage and the diode. So with the forward bias of the diode. So even you can check in the mode 1, when I turn on the switch, the diode is going to be in the reverse bias, because the supply plus is connected to the diode cathode and the supply minus is connected to diode anode. So the diode is in reverse bias mode. So it is in off state. So when I turn on the switch, the diode condition is in off state. Whereas when I turn off the switch, diode comes in forward bias with the discharging current of the inductor, because there is no other go. So the discharging current of inductor makes the diode to be in the on state. So that time, ideally, I can say the voltage across the diode can be make it as 0. So now again, I am trying to apply KVL here. So remember one thing here, the polarity I'm going to consider as a reference. So in practice, the polarity gets reversed, because here, if you see, inductor is in charging state, current is entering into positive polarity. Here, in second picture, inductor is in discharging state in the mode 2 condition. Inductor is in discharging state. So the current should leave from the positive. So actually the polarity gets reversed. The voltage across inductor becomes negative. Voltage across inductor becomes negative. To see that negative waveform, the negative polarity in the graph, so I'm going to take a positive reference here, negative reference here. So you can take this as like this. You can take a red wire here and you can take black wire here. So always, if you want to check the waveform across any element, you won't be changing at regular instance, right? So you'll be connecting a red wire to one point and the black wire to other point. So there you can check the waveform in the DSO. So the same thing here I am doing. So positive polarity I am fixing here as a reference, and negative polarity I am fixing. So in reality, the polarity across the inductor is going to change. That you can see in the equations when I write a KVL equation. So again, I'll try to write a KVL equation with the reference polarity only, so that I can see the negative voltage across the inductor in the equation. So if I apply KVL here, so minus VL and then minus V naught equal to 0. So again, from this VL equal to minus V naught. So from this I can justify in the equation, I can see the negative polarity of the inductor. Okay, so you can see when the switch is in off state for a duration of T off, the voltage across inductor becomes negative. So VL equal to minus V naught, and the inductor is in discharging state with the falling slope, from the Imax to Imin, Imax to Imin. Okay, so again this process gets continuous. Again when I turn on the switch here, so again the inductor starts charging with a gate pulse applied at the switch point to the switch gate. Again, when I turn off the pulse, when I turn off the switch, again the inductor is in discharging state. So this continuously repeats. Okay, now you can check here the graph of inductor current and inductor voltage. Okay, and also we have written equation, voltage across inductor during switch on state is Vs minus V naught, and whereas the voltage across inductor during switch off state, here the switch is closed, whether here it is in on state, where here the switch is open, the switch is in off state. So this is a mode 2 where the switch is in off. Here it is a mode 1 where the switch is in on. So we got two inductor voltage equations. So one is Vs minus V naught during on state, one is VL equal to minus V naught during off state. So now our main goal is to find the output voltage. To find the output voltage. So here one relation we are going to follow to derive the output voltage, that is average voltage across inductor is zero in a complete time period. So why this is valid? Why this is valid? This condition is valid means, the inductor never consume uh, energy. It never consume power. Okay, so it acts like a storing element. So once the energy is stored, again it gives back to the uh, load or source. So it is never going to consume. Inductor never going to consume. So it just like a storing element. So and again it gives back. So if you see during on state, when the switch is in on state, so the voltage is going to be positive, and also the current is positive. So if you see the product of voltage and current, which is power, so power is positive. Power is positive. Now come to mode 2 where the switch is in off state. Now you can check inductor condition. So the current is positive here and the voltage is negative. So, so if I take a power, it is a negative. So here in the mode 1, power is positive. In the mode 2, power is negative. If you take average of inductor current, definitely it is having some value. It cannot be zero. Average of inductor current cannot be zero. By seeing this equation itself, you can say. But there is a chance of making average of voltage equal to zero, so that the voltage average multiply with the current average, you can make it zero. So voltage average must and should be zero to satisfy the condition that inductor never consumes uh, power. It never consumes power. So definitely the inductor voltage average value should be equal to zero to make the statement valid. So that is why the statement is valid for all the converters analysis, and also based on this statement only we are going to derive the output voltage. Not only buck converter, it is applied for all the converters, all the modified converters also, which is there in the research. So now we know the voltage across inductor is Vs minus V naught during on state, that is T on. So average voltage across inductor 0. That means how I can write. So the area under this curve. So Vs minus V naught I can write, and after that it should be multiplied with the T on time duration. So this T on I can replace with D into T, where D is called as duty ratio. So D I can give D as T on by T. It is a factor. It gives information how much percentage the switch is in on state in a complete time period T. So D I can give as T on by T. So T on I can write it as D into T, where T is the complete time period T, capital T. So this I can write it as Vs minus V naught into dt. So this gives you area under the curve during switch on state, voltage across inductor during switch on state. Now come to the mode 2. So this is the area under the voltage inductor voltage curve. So where it is given as minus V naught into T off. So this duration I can make it as T off. Okay, so now how I can write T off? T off I can write it as T minus T on, because this is total time period capital T. So if I subtract T on from the capital T, so capital T minus T on. So here T on again I can write it as D into T. So if I take t common, I can write it as 1 minus t. So this t of I can write it as 1 minus d into t. So minus V naught into T of, that is minus V naught into 1 minus D into T. So this is the area under the voltage, inductor voltage curve during off state. So total area, okay, divided by a time period, complete time period, so equal to 0. So this equation you are going to write for the buck converter. So in generalized manner, I can write like this: voltage across inductor during on state into D into T plus voltage across inductor during off state into 1 minus D into T total divided by T. So when you totally divide with a T get cancelled. So no need to consider capital T here, equal to 0. So you need to substitute VL on for your particular converter. So it may be a buck converter, boost converter, or buck boost converter. So here in case of buck converter, we found what is the voltage across inductor during on state. I can write it as Vs minus V naught. Whereas the voltage across inductor during off state, I can write it as minus V naught. So if I try to solve this equation, I can able to get the output voltage as V naught equal to Vs into D. So again, we already saw that the duty value is going to be uh, T on by T in terms of equation. So from this equation, I can say that the duty value is less than or equal to 1. So T on maximum, it can reach till capital T. So that's why the duty value is less than or equal to 1. And from this equation, I can say that the output voltage is less than or equal to Vs. So maximum, we are not going to operate at a duty equal to 1. So we'll be operating below duty equal to 1, that is duty less than 1. So definitely the output voltage is less than Vs. So the output voltage is less than supply voltage. So that is why we call this type of converter as a buck converter. So the circuit we derived is a buck converter, is a buck converter. So it is doing the output voltage a step down compared to the input voltage. So this is what about the buck converter. And from this buck converter, we from this analysis we came to analysis that one important point we discussed is the average voltage across inductors 0. So from this again I can say that so the minimum current is equal to uh, in the state like mode 1 again that value is equal to the next cycle minimum current. So always this minimum current should be equal when you pass from one cycle to another cycle. So then only I can write this statement, you know, V equal to LdA by dt, LdA by dt. So from this I can write I equal to 1 by L. So di I can write it as di equal to 1 by L V into dt. So if I apply integration both the sides, so from t naught to if I do check from t naught to t, where t naught is the initial time here, t naught to t. So I can write I of t naught to t naught plus t. Sorry here. So t naught to t naught plus t. So here also t naught to t naught plus t. Okay, so like this. So again, if I apply integration here, so I can write I of t naught plus t minus I of t naught equal to 1 by L integral t naught to t naught plus t VL dt. So from this, I can say that so the minimum current at the first cycle, that is I of T naught. If I take this as a the minimum current as I of T naught here, so it should be equal to the minimum current at the next cycle I of T naught plus T here, I of T naught plus T. This is I of from here to here. So T naught plus T, T naught plus T. If I take T naught, it becomes 0. T naught equal to 0 if I take, then I of 0 and I of T should be equal. So it is going to be equal. So from this I can say average voltage across inductor equal to 0. So it is valid for all the converters. Similarly, you can see for the capacitor also, the average current through a capacitor over a one period equal to 0. So we know I equal to C dV by dt, C dV by dt. So from this I can write dV equal to 1 by C into I dt. Again, if I apply integration from T naught to T naught plus T, I can write the voltage after applying integration. The voltage I can write it as V of T naught plus T minus V naught minus V of T naught plus T minus V of T naught equal to 1 by C integral T naught plus T T naught to T naught plus T I of dt equal to I dt equal to 0. So from this, I can say that so when the capacitor voltage is charging, like when the voltage is rising during charging state, so it should be again discharges again it will charge in another cycle. So this minimum point should be equal to this minimum point. So that is what V of T naught plus T equal to V of T naught. So with this, I can say the average voltage, average current, because this becomes 0. So the again, if you just multiply with C by T, I can get this expression. From this expression, I can say that uh, the average current through a capacitor over one period is equal to 0. That is the capacitor current during on state into T on plus the capacitor current during off state into T off equal to 0. Again, you can say T on as a dt and T off as a 1 minus d into T. So now let us see what is going to happen with respect to buck converter. So now in case of buck converter, let us see the capacitor current in mode 1. So what is the capacitor current in mode 1? I can write capacitor current as IL minus I naught. So where I naught is here, where I naught is here, and IL is here. So I can just apply KCL and I can derive capacitor current as IL minus I naught. Now let us see for the mode 2 where the switch is turned off. In this case also the capacitor current remains as IL minus I naught. So if I apply the rule average current through capacitor is 0 over a time period, so the same equation I can take IL minus I naught into D plus IL minus I naught into 1 minus D. So T it is going to cancel over a time period T. So here I'm not writing a T here. So from this I can say that IL minus I naught equal to 0, then IL equal to I naught. So from this, what is the inference we are getting is the average inductor current is equal to output current, that is the load current. So if you see the graph here, so the output current is IR, that is a load current. So the average of this curve is equal to which is given in the dotted line. So that is equal to the load current. IL average is equal to output current, that is IR. So now let us see the capacitor current. Let us see the capacitor current here. So how the capacitor current need to be drawn. So IC, you know IC equal to IL minus I naught, IL minus I naught. So now if you see this particular instant till here, so IL is less than I naught. So I naught is given by output current, average output current, this that is IR. You can write it as IR or I naught. So the output current I naught is greater than IL. If you see this particular instant. So that is why the capacitor current is in negative direction. So wherever the output current is equal to inductor current here at this particular point. So the capacitor current is 0. Again, in this particular duration, till this particular duration, IL is greater than I naught. I naught is here, IR is here. So IL is greater than I naught. So that's why the curve follows the same shape but in the positive direction. So again in this particular point, IL equal to I naught. So the capacitor current is remains 0. So this follows the same thing. So this will be in a repeated case. So it will repeat. The same curve gets repeat. So this is how you need to draw for the capacitor current. So again from this I can say that for capacitor, how I derived IL average equal to I naught means by following the principle, always the average current through a capacitor over a period is 0. So similarly the average voltage across an inductor over one period is 0. So that is what you need to remember for all the converter analysis. So again, so we have seen the output voltage is equal to Vs into D. So now how to design the value of inductor and capacitor. So once the converter is given, specifications are given, so you should be able to design the value of inductor and the value of capacitor. So let us go for the mode 1 case. So we have written voltage across inductor as Vs minus V naught. So you know VL I can write it as L into del I by del T. So from this del I can write it as Vs minus V naught divided by L into del T. Here the change in time where this equation is coming during mode 1 case. So what is the change in time here? T on. So T on, how I can write? D into T. So I can write del I, the inductor ripple, current ripple, inductor current ripple, del I during this particular case, I can write it as Vs minus V naught into D T divided by L. So you can write it as with respect to frequency also. If I send this capital T to the denominator, it becomes F. So I can write it as Vs minus V naught into D divided by LF. LF. So where F is the switching frequency. So from this, the specific user is going to specify what is the ripple current value and what is the input voltage, what is the output voltage, what is the switching frequency required, and what from the output and voltage and input voltage relation you can calculate the duty. So from this particular relation you can able to find the unknown value L. So this is how you need to design a value of inductor for a converter, for a buck converter, for a buck converter. So here all values are known to you because this is going to be specified by user, and Vs V naught are going to be specified by user, and required duty to maintain V naught as a function of Vs you can able to calculate. 2T is a switching frequency, T 1 by T is a switching frequency. So if they give switching frequency, directly you can calculate T, or else you send this T to the denominator. That is what equation we have seen. You can able to calculate the unknown value of L. So this is how you need to decide the value of L required to maintain the particular value of inductor current ripple. So this is how you need to design the inductor value. So then come to the capacitor. So capacitor, how I need to design. So we already seen the capacitor current nature waveform. Okay, so you can check here the capacitor current is positive in this particular area. Okay, so the charge stored in this particular instant, okay, change in Q, I can write it as C into change in V. From this I can make it as change in V equal to change in Q del Q divided by C, capacitance value. So I can able to calculate del Q. If you see this triangle here, so you know the area under the triangle. So half into length into breadth, half into here the length is del I by 2 here. So it should be del I by 2 here. So because this capacitor current came from inductor current only. So inductor current we mentioned the ripple as del I, peak to peak ripple. So half of that comes as del I by 2. So half into length as del I by 2 and the breadth if you see t by 2. So from this I can say del I into t divided by 8. So now this change in Q I am going to substitute here in the del V. So I can write it as del V naught equal to T into del IL divided by 8C. Del IL you already know, del IL you already know, or else you can simply substitute del IL equation here. Del IL you already know. Okay, T you already know. Based on switching frequency, you can calculate the T value, and del V is going to be specified by user. So the unknown value of capacitance you can able to calculate from this design equation. So this is how you can able to decide how much value of capacitance required to maintain the output voltage ripple, particular value of output voltage ripple. So this is how you need to design the values of L and C for a buck converter analysis. So now let us see the discontinuous mode of the buck converter. So what do you mean by discontinuous mode? So let us see here this graph what we have seen. So let me draw the same graph here in this particular page. So now when the switch is turned on, inductor is charging from the Imin, okay, and when the switch is turned off, inductor is discharging from the Imax. So and this repeats, and this is repeating, okay. So now if I want to calculate Imax, so Imax is here, Imax is here, okay. So now if I want to calculate Imax, so this is IL average, IL average. So Imax I can write it as IL average plus del I by 2. So because the total ripple is del I, here the total ripple I can make it as del I. So half of the ripple comes here del I by 2 here, and here del I by 2. Okay, I can take another color here. So here I can write it as del I by 2, and down also the same thing del I by 2. So now from this I can write Imax as a IL plus del I by 2. So similarly, I can write I min. From this equation, you can able to find the maximum value of inductor current. You can able to find because IL average is equal to I naught, and del I formula you already know. From this, you can calculate I max value. Similarly, I can write I min also. I min how I can write means this is IL length, IL length. This total length is IL. From this, if I subtract this del I by 2, down del I by 2, then I can get this value, I min value. So I min I can write it as IL minus del I by 2, IL minus del I by 2. So now what is mean by discontinuity mode means, so where you can check this graph, again you can see this graph. So what I'm going to do here is inductor current is just touching the axis, x-axis. So again, I'm going to draw another graph. You can check this graph. So inductor is charging, inductor is discharging before reaching the total time period, capital T. And after discharging, reaching the discharging point where the current is zero, so the inductor current is fully zero till this in this particular duration. So this is what discontinuous mode of operation for the particular converter. So now this is continuous conduction mode, and this is discontinuous conduction mode where the current is zero, inductor current is zero for some duration, So this is the boundary case where the current is entering into discontinuous mode. So now we'll try to figure out if what value of inductor the current is going to just touch the axis, horizontal axis. So if you try to maintain the inductor value above that particular L critical, so you can go in continuous conduction mode. So you can operate in continuous conduction mode. Suppose if the value of L critical inductor, the value of L is less than the critical inductance value, then definitely you are going to enter into discontinuous mode. So I need to figure out what should be the value of L for which I can maintain the current, above which I can maintain the current continuous. Minimum value of L required. So I'm going to take the same equation, I min equal to IL minus del I by 2. So if I see this particular graph, second graph, at this particular point, just it is touching the axis. So I min value is 0. I min value is 0. So the same equation I am going to write here. So putting I min equal to 0. By substituting I min equal to 0, then I can write IL minus del I by 2, I min minus del I by 2 equal to 0. From this I can write IL equal to del I by 2. IL equal to del I by 2. So you already know what is the IL value. So IL equal to I naught. IL equal to I naught. So from you know the value of del I also. Del I we already derived in the previous discussion what is del I value. So you know IL value. So you can able to figure out the value of L, critical value, minimum value of L need to be maintained for the continuous current, So by seeing this, you can check by solving this, you can able to figure out the minimum value of L required for the continuous current. So even you can see this mathematical analysis here. So I mean equal to 0. Uh, so then this should be equal to del I by 2. So del I by 2 you can see here. V naught, if I take common this one. Uh, so this is what it is there. Okay, so from this you can able to calculate the value of L. So no need to remember this formula also. Just you can do one thing. Just make it as IL equal to del I by 2. Since I min equal to 0, so IL equal to del I by 2 from this relation. So by simply substituting the value, we can able to get the minimum value of L required. So I can show here this IL equal average equal to I naught, that is equal to V naught by R, and after that del I is what we have written, Vs minus V naught into D divided by 2 into LF. Del I is Vs minus V naught d by LF. You might be seeing with respect to T, where it is in the numerator. When I change this, when I bring this T to the denominator, it becomes F. Okay, so now what is the unknown term here? L. Because load resistance you know, V naught you know, Vs you know, V naught you know, duty you know, based on output voltage and input voltage relation. So the unknown value is L, that you can calculate. So this is what you can calculate. If I try to derive here also, you can check here. V naught equal to D into Vs into D, okay, divided by 2LF equal to V naught by R. Uh, so from this, you can take a Vs common here. So V naught by R equal to Vs into 1 minus D into D divided by 2LF. So anyway, Vs into D is equal to V naught. So this one get cancelled. So from this I can write it as 1 by R equal to 1 minus D by 2 LF. So from this I can write L as 1 minus D into R divided by 2F. The same thing here it is mentioned. L equal to 1 minus D into R divided by 2F. So this is how you can able to uh, calculate the critical inductance value. So no need to remember the formula. If there is any problem here, directly you substitute the value of IL average and del I. So for del I, you take L as unknown, and you need to figure out the value of L from the equation. So this is how you can able to do the discontinuous analysis. You can able to figure out the value of L for which the current maintains continuous. Minimum value we need to maintain, inductor value we need to maintain. So now what about the output voltage? When the inductor current is in DCM, discontinuous conduction mode. So again, come to the picture. Come to the picture here. So here I am drawing the picture, inductor current here. So inductor current over a time duty. If I take turn on duty as T on D1, okay, so inductor is rising. Okay, so once I turned off the switch, inductor current is discharging. Okay, after the it is not reached to capital T, but it is discharged earlier itself. So after discharging instant, after fully the inductor current is discharged, the inductor current remains zero until the time period completes until the time period completes. So that time the voltage, definitely the voltage across inductor also zero, because if there is no current flowing in the inductor, definitely the voltage across inductor also zero. Now let me apply KVL and also the principal average voltage across inductor zero. So when in case of mode 1, in case of mode 1, when I turn on the switch, so VL is given as Vs minus V naught. Here it is mentioned as VDC. So you can take Vs, VDC, both are same. So when I see the inductor voltage in the mode 1, I can write it as Vs minus V naught during mode 1. What about mode 2 case here? In the mode 2, when I turn off the switch, the inductor is in discharging with the turning on of diode. So that time I can write it as VL equal to minus V naught, minus V naught, minus V naught, and this should be done at the mode 2. This should be done at the mode 2. Now, here there is one more instant is there where the inductor voltage is zero, because inductor current is zero, and again inductor voltage is also zero. So if you take that particular instant as a representative with a time of d3 into t. Here you can check the three divisions in the modes: d1 into t, that represents mode 1, d2 into t, that represents mode 2 where inductor current is discharging, d3 into t, that represents mode 3 where inductor current is 0 and inductor voltage is 0. Again, if I apply average voltage across inductor 0, that is VDC minus V naught into d1 t. Anyway, t gets cancelled, that's why it is not mentioned. Okay, again uh, uh, plus minus V naught into D2, that is with respect to mode 2 inductor voltage area. This is a inductor voltage area at the mode 1, inductor voltage area at the mode 2 plus 0. So from this I can see the output voltage as in this equation form. So V naught equal to D1 VDC by D1 plus D2. So V naught equal to D1 VDC by D1 plus D2. So what is the inference from this? So you can check carefully here. V naught equal to D1 VDC by D1 plus D2. So what is the inference here means? If you take with respect to continuous equation, V naught equal to dVDC. Okay, so if you just compare the continuous conduction mode output voltage and the discontinuous conduction mode output voltage, you can verify that the output voltage in discontinuous conduction mode is going to be higher when compared with the output voltage in the continuous conduction mode. For this, I am going to give with a simple numerical example. Let me take a duty is 0.5. A duty is 0.5. Okay, so in the continuous conduction mode. Okay, so then output voltage is going to come as B naught equal to 0.5 VDC. 0.5 VDC. Now, in case of second condition, DCM analysis, take D1 as 0.5, D1 as 0.5, and the D1 plus D2 is equal to 1 minus D here. Okay, 1 minus D1. So now, sorry, D2 plus D3 equal to 1 minus D here, 1 minus D1 here. Okay, so now let me take a D2 as uh, uh, D2, you can take it as let me take here D2 as a zero point 0.3, for example, and D3 as a zero point 0.2. So you can see the total summation is equal to 1.5 plus 0.3 plus 0.2. It is going to be equal to 1. So now you substitute these values in this equation. So 0.5 VDC, that is D1 is 0.5 divided by D1 plus D2. What is D1 here? 0.5 plus D2 is what we considered, for example, 0.3. 0.3. Now you can check in the calculator. So what is the value of zero point 0.5 divided by 0.5 plus 0.3? 0.5 plus 0.3. So from this you can check that the output voltage is coming as 0.625 into VDC. So if you compare the continuous conduction mode output voltage, discontinuous conduction mode output voltage, you can see it is clearly justifies that the discontinuous conduction mode output voltage is greater than continuous conduction mode output voltage. So from this I can say that buck converter, if you operate in DCM, the output voltage is going to be greater than uh, in the which you can compare with respect to continuous conduction mode. Even I can able to prove with respect to the graphs also. So this is the graph we have seen, right? With respect to continuous conduction mode. Suppose if the discontinuous conduction mode is seen, let me take discontinuous conduction mode here. Let me take the discontinuous conduction mode. Okay. So now if the discontinuous conduction mode is seen, what is going to be happen? So in continuous conduction mode, let us maintain the same area. Okay. So I already explained that average voltage across inductor is 0 for all the converter analysis in any case. Now, if I operate in discontinuous conduction mode, uh, then the output voltage in the mode 2 is going to be 0 here itself at this particular instant. That is what we have seen. Then this area is definitely, if I say in continuous conduction mode, if this area is equal to this area, then as I'm reducing the area, right? So definitely this area, definitely it is going to be this area is not equal to this area. So to make the area equal, you need to increase the magnitude in the vertical way. Okay, magnitude definitely you need to increase to make this area is equal to this area. So there you can see that the output voltage is increasing with respect to continuous conduction mode. With respect to continuous conduction mode, the output voltage is here, but whereas with respect to discontinuous conduction mode, the output voltage is little below, that is higher than continuous conduction mode, because to make the condition satisfy, average voltage across inductors is 0 in a complete time period. So in previous case in continuous conduction mode, we said this area is equal to this area. Now you can see as current is 0 at this particular point, so the output voltage becomes 0 here itself. Sorry, the inductor voltage is become 0 here itself. So now definitely the length has to increase to make this area equal to this area. So there you can observe that the output voltage is going to be higher in DCM compared to CCM. So in this video lecture completely we discussed about buck converter analysis. In the coming video lecture, we'll see about the boost converter. Thank you very much.